I don't expect quite somebody that close when I talk. So I'm going to talk about communicating delay-sensitive and bursty information over an outage channel. This is a work mostly done by my student Samsak Katipiakol, who is close to finishing up, and a postdoc, Petrus Elia, who was visiting CalIT last year. So I put a lot of stuff, so I'm going to go down and see how much I can cover. Most probably I won't be able to cover everything. I'm going to give a quick intro, sort of motivating the problem in its more realistic and more non-asymptotic regime, try to motivate the problem, say what is the problem when you try to apply Shannon Theoretic approach, and then sort of go to high SNR analysis where we found we could get some nice insights into the solution. And then I apply it to a particular problem. So let me do a quick review at the cost of possibly boring everybody. So if you think about a joint source channel coding problem from, Shannon's, very well-known paper, we have a sequence of symbols that are sitting in an encoder, and I ask myself how to encode them to pass them through a noisy channel, get them at the decoder, then decode them back. And the question that classically posed in information theory is, how do I actually do this, and can I do it in separate ways, source coding first and then channel coding and so on. But if you think about real applications, time matters for me. So these symbols that in information theory sort of sit there as IID replicas of some random variable, these guys are not there at any time when you start the operation. They in effect arrive at different times. So here I sort of try to map these sequence to a timing sequence. So at time tau 1 equal tau 2 equal tau 3, three symbols at the same time arrive, then nothing arrives, then V4 arrives, Vn. So I have some dynamic in the system, and then I get a bunch of these these symbols and put them in a block of code and send them over a noisy channel. I receive them at a time which is somewhat related to the length of the code that I pick. So if I pick a n channel used to transmit this information, this n delta is how many times I use the channel. Then I get at this time a vector of yn, and then I decode that to get v1 hat to vn at a particular time, sigma of n. So if you think about it, the delay from the perspective of any real information sense will be the moment that each of these symbols arrived here to the time I actually decoded them. So that is an important phenomenon. So unlike in classical Shannon theory, where you assume that so long as I get those replicas and they're close to this is a good decoding scheme. In real application, if this time takes to be 10 years, then I really don't care about particular weather forecast about 4 days ago that was sent out, right? So actually, I'm trying to make the case that you really want your definition of error to include both all those symbols that you don't quite get, as well as those symbols that arrive after a certain deadline. And of course, this is the simplest inclusion of delay model.
So but your error is if either of the i's is over the delay.
So this is the simplest way I can sort of modify the old model. I say if any of the symbols I received is an error, or any timing between the two that I received is larger than d. Of course, this is very particular to a particular application, but this would be a threshold type delay. So let's see what happens and how the burstiness and the sort of the traffic pattern matters in if I want to optimize or if I want to minimize that probability of error. Let's say I have two scenarios of bit arriving. In the first scenarios, all symbols arrive. Let's say 100 bits arrive all at the same time, and then again 150 milliseconds later another 100 arrive. So it's very regular, both of the examples, versus the second example where they all arrive in a constant bit rate, the 100 bits, then there's an off period, then again 100 bits, right? And I want to ask myself, how can I make sure there is no delay violation while I'm getting the same performance in terms of error? when you try to solve the first problem, obviously you get all these bits, so you get 100 bits. You have 150 seconds, so you can form a block code of rate 2/3 and code these guys, send them over the channel, and this is the decoding time. By the time these guys are decoded, you get the next block and you send them, right? So this is sort of what you would do. But the second guy becomes more complicated because these guys have now arrived long time before this guy. So if I use the same technique for here, the delay for this first bit when it gets to here will be 200, 300 milliseconds. So that's not going to be acceptable. So you will, in fact, if you want to guarantee a delay of 150 seconds, what you will have to do is to break the codes in much smaller pieces. So in fact, you get 50 of them, you use the same 2/3 code, and you decode them here. Then the next block gets ready, you code them, you decode them, and so on and so forth. So this is only when I have a deterministic pattern of arrivals, but it's just I have them spread over time. Now, if you add randomness, so what do I mean by that? Here I had to give up on the coding block length just because I wanted to deliver the data in the timely manner. I'm just saying, this is 100 bits here. Yeah, sorry, I should have written it. 100 bits here, and then I have 150 seconds. I just made it up again. Right, so I'm saying if I keep the coding rate the same, I have to shorten the block length, which means, in effect, I am seeing a lot less realizations of the channel, so the probability of error will go higher. Right? So that's sort of the intuition. So it's not surprising. Intuitively, I have 2 degrees of freedom. How long my code is, and what is my coding rate relative to the capacity of the channel. And the trade-offs are fairly easy to imagine. If I increase the length of the code, I get to see more and more realizations of the channel. So the channel will look more and more typical, right? Which means that I can actually get data much closer to the capacity, or from a delay sense, I can do better. So increase reliability by increasing T. But as I increase T, as we saw in the previous example, you need more channel use, so your delay would go up, right? So you need you can only really accommodate burstiness if your delay requirement is much larger than the block length that you choose. Again, the trade-off in terms of R is the same. If I get close to the capacity, then I'm going to shove data faster out, so my delay is going to be good. But if you think about random coding error exponent or any equivalence thereof, as you get closer to capacity, your probability of error will do worse, right? So intuition says we should be able to sort of trade these guys off. Unfortunately, I have not seen this to actually be, in fact, well articulated in the literature. The one thing that seems to be a folk theorem, all of us believe, goes back to the notion of capacity of the channel, and goes as this: if I have arrival rate of symbols arrive with rate lambda, and each of them have entropy h of v, so long as lambda times h of v is less than c, then I can do the simplest scheme possible. The simplest scheme and all of the communication systems that you can think of, the symbols arrive, I just buffer them up to collecting n symbols or t symbols. Then I put them in a code, send them over the channel, right? And there seems to be a folk theorem that says, okay, any rate such that lambda h of v is less than c, I can just do the classical separated scheme of queue the bits, then code them for source coding, code them for channel coding, send them over the channel, and everything should be good. Notice that it's not surprising that you want the number of channel used to be roughly half of the delay time, right? So if I need at least half of that time to send these data, and half of them are the bits that are arriving, just like the example I showed you, that are arriving and waiting for their turn to be transmitted, right? So this scheme, although there's a lot more math to concretely define the scheme.
Can you go back one slide?
Sure. This one?
So therefore, by queuing, are you sort of implying some kind of scheduling? Or?
No, this is first come, first serve.
Okay.
But I'm just saying, I'm just going to first come, first serve, back them up until I have enough of them, send them. So infinite queue line. Right? So that simple scheme will actually guarantee that in the asymptotics, if I relax the condition of D going to infinity, then I can guarantee the probability of error in this new definition, which now includes both the errors over the channel as well as the errors due to violating my delay. This one I can guarantee to go to 0. Right?
And this D by 2 is it for any burstiness of the source?
Any burstiness of the source, you can guarantee this, and that's the beauty of the separation. So, and that's actually, I'm interested if anybody has seen this. It seems like everybody believes that that would be the case, so long as your arrival rate is exogenous to your channel, right? So all the good assumptions, all of the inter-arrival times is exogenous to the source entropy and the channel. What I mean is that you don't have a TCP type traffic where if the channel gets bad, you back down, and if you can get into chaotic behavior if you actually have a closed loop system. Yeah, no, there's no scheduling. Yeah. So the rates, everything is sort of fixed in all of these schemes. And actually, if anybody has seen anything like this, I have a couple-page correspondence write-up of this, but I just can't believe there is no such thing in literature, so I keep sitting on it. My students getting really annoyed. But so if you have seen anything like this, so this is the level. The problem is all of these asymptotics rely on sending the delay requirement to infinity to get even the separation principle whole, right? So if I want to solve the original problem, I have to send my delay requirement to infinity to get any meaningful result here, even in terms of block. Now, if you get fairly good tight bounds on channel error exponent, you can also get some bounds on the delay violation probability. You can go for balancing these two and get at least the optimal coding rate figured out. But you will not be able to solve the question of how much of my delay budget do I allocate to smoothing out the channel atypicalities, how much of it for smoothing out my inner arrival atypicality, right? So when I queue things, what I'm doing is I'm averaging out the inter-arrival times for symbols to arrive to go around their mean so that I can pump them up in a constant bit rate fashion. And when I actually code them on long blocks, also I'm averaging over all the channel realization. And this just says if you have enough degrees of freedom, you can do both. So far, that's all I know. So from now on, I'll try to be a little bit more precise about what my model would be and how we solve this for the high SNR asymptotics. So I have a source. I have a buffer that collects the symbols that come here, and I'm going to assume the source is binary, good old Bernoulli IID. Source coding, I relax that. So bits arrive according to some stochastic process. It could be any general stochastic process. I buffer them, then I encode them, send them over a particular channel. For the purpose of this talk will be outage channels. Then I decode them. If the mutual information, if the channel is in a bad state and cannot sustain the mutual information, there will be losses. So I throw those guys out. Then I sort out all the symbols that I have correctly identified and figure out which ones are beyond their delay limitation, their delay constraint. I throw those out. So these are the sources of loss in my system, and I look at how to optimize the performance of this system. Right? I am assuming that there is no feedback, neither in terms of channel state information nor in terms of retransmission request. So, and that's an assumption that we make. So channel coding, I'm going to assume happens in blocks, a regular block coding scheme. So each code word spans over T uses of channel time. So now if my code rate is R, I'm taking RT bits out of my buffer and I'm sending them over the channel with T use of the channel. And then I'm assuming that the decoding does not happen bit by bit. The decoding happens one at a time, just because the model seems to be simpler to handle. Now the queue as a result becomes a batch service queue. I take RT every T seconds and I just send them out, right? And I'm interested. as I said, the overall performance are either because of decoding error or violating a delay bound, and the rate of these events occurring are a function of the two important parameters I have: the coding length as well as the coding rate relative to the ergodic capacity of the channel. So the question is, how can I choose R and T such that this total probability gets to be optimized? If I assume the channel is exogenous to the, to the arrival process, then these two events are independent from each other. I can write it as such and try to optimize it. Okay?
You would assume that something will be in error as well as violating the delay?
Yeah, it could be. This would be so I get this plus this minus both events happen. But that will assume that those events happen independently, right? That's all. You'll see that this won't be important because I'm going to a large SNR asymptotic. So this nicely captures the intuitive explanation that I gave, which is the probability of channel error is increasing in R and decreasing in T, and vice versa for probability of delay violation. So you already see the trade-offs that we were talking about. So if I could solve this, then I think something fundamental can be said about how to design networks. But I can't solve this. In fact, trying to go for delay-sensitive information theory is not something new, and there's a large body of literature that people work on zero delay information transfer and real-time encoding, decoding, or delay-less information theory. This is the first work that I could track down. Is done by Drake in 1962, but it goes up to even at ITA, Mohajan and Tanaketsis and Shannon and Yüksel. A lot of people have been looking at. This is a control theoretic formulation of the problem. When you get a bit, you have to deliver it, the next channel use. So this is called zero information. Linder and Zamir and Weissman, they have done the source coding version of the problem, and some people have done the channel coding version of the problem. But what happens is this is the opposite extreme of Shannon Theoretic result, in the sense that now every bit will see only a very few uses of the channel, so there is no typical sequences that can arise, there's no equipartitioning that you can use, so it becomes a very sort of stochastic control formulation, or information theoretically, but it's a very tight budget in delay. So I want to go away from this and sort of see if I can still average certain things out and sit on lucky events of typical events. So this is the main difference. And then I would like to say there is a larger body of work when you have feedback. If you have retransmission request, or if you have channel state information, you can actually change the problem slightly and write different versions of that. So that's I'm not going to talk about that, or that's not in our model in some ways.
So in those work, what is the metric? Is it probability of error?
In all of these works, when you have in all of these, you don't have a probability error because you're retransmitting, right? So their models is delay versus energy, delay versus, depends on the particular model. Right?
And there's no feedback?
When there is?
And there's no feedback, what is the metric?
Yes, it's going to be probability error, what I put up, right? This guy. When there's no feedback, you are going to be lost. Unless you solve the zero error channel capacity problem, you are going to be doing some probability of error, right? So, what is the motivation of of my talk today? Well, I'm really going slow. The motivation is trying to understand how the work that Li Zhang and David Shea did motivates our work in the sense that if you think about sort of classical Shannon theory, all the asymptotics occur in large times. You just increase the block size and you get asymptotic results. And Zhang and Shea showed a different regime for outage channels where they looked at large SNR. So they look at problem indexed by SNR, and they say as SNR goes to infinity, how can I characterize the performance over the channel? How can I set up bounds? So they defined a data rate, which is a function of SNR. So now I have problems indexed by SNR, and I have an average error probability, again, indexed by SNR. Now I define a family of codes for these different SNR indices to achieve a certain multiplexing and diversity gains if they achieve the following. So I know that data rate RSNR at the capacity scales with log of SNR, right? That's the capacity scaling for the outage capacity. So I look at the proportion of these two, and I call this to be the multiplexing rate, as well as then I say the probability of error over the channel is a function of SNR. I'm going to look at how it scales with log SNR in the exponent. So this is the exponent of my error with respect to SNR, right? So roughly, it's a good way to think about it. The probability of channel error is SNR to the minus diversity of the channel. And they showed for different channels, you actually get a fixed relationship between D and R, which is given by a curve. So they, for example, for a fast fading SISO channel with block length T, they showed that you can achieve exponent of T1 minus R if you operate at rate R. Right? So if you scale your data rate as R log SNR, then the probability of error will go to 0 with exponent with a negative D channel. Right? Is that clear? So I'm going to use the same sort of mindset to actually motivate my problem. So now my goal is to do the same thing. Is my goal to index my problem with SNR and find the asymptotic total probability of error in terms of this large SNR. Okay? So the best hope is that I can show that the delay violation also decays with SNR exponentially fast. That's the best I can do because I know channel is not going to go to 0 anything faster than exponentially with SNR. So my question becomes, can I actually manage to find a similar expression for delay violation? Right? So the question is it always possible to do that? If it is any time possible to do this, can I actually match the two exponents to arrive at an asymptotically optimal solution? Okay? So I'm sending SNR to infinity. So now if you think about the queuing system that I have, I'm taking bits out, and I'm sending the capacity of the server for that queue to infinity. To keep the problem meaningful, I need to make sure the loading of the system doesn't go to 0. If I have a finite arrival rate of symbols coming in, but my channel capacity is going to infinity, obviously, I will very soon get rid of delay violation, right? So in order to keep the problem meaningful, I'm going to make sure that my arrival rate also scales with log SNR. Okay? So this is the regime I'm interested in. So I'm going to give you a hand-wavy argument here, and then if we get through, I'll show you a little bit more concretely the math of it. So what turns out, all I said, the constraint is that the expected value of the arrival process should scale with log SNR. Of course, this is not enough to describe how the arrival process scales. So there's no unique way to do it. Let's look at a couple examples.
So, but I thought you were assuming sort of the arrivals are exogenous to the channel, right? So
yeah.
What is the intuition behind, what does this really mean physically?
So I'm assuming that the system as a whole is going to a higher and higher SNR regime, but the demand on the system is actually growing also. Right? In order for the problem to be meaningful. If my channel capacity goes to infinity and I have a finite arrival stream, obviously there's no problem to solve. Right? The delay would go to 0 very fast.
So essentially, as your system gets better, you're saying sort of the demand gets
better. The demand gets better too, right? So they're still exogenous, they're just proportionally scaling. So let's look at a couple examples. So I could do a really simple way of scaling my arrival. I say the arrival process is some A of t so long as the log SNR or the SNR is small, or if SNR gets large, this is going to be a deterministic process with arrival log SNR bits arrive deterministically. Obviously, in this system, the delay violation very quickly becomes irrelevant. As soon as the log SNR gets large, there's nothing to do. The arrival process is actually deterministic. You assign half of your delay budget to this guy, you're done, right? So that's not interesting. I could do the opposite. I take an arrival process and modulate it by log SNR. This guy, again, will not be interesting because I have a queuing system. The server capacity is going to infinity, but all the stochastics remain. So probability of deviating any delay will be a constant and will be irrelevant to the problem. So I get nothing. On the other hand, if I look at the arrival process to scale in the following way, let's assume it's the summation of a bunch of arrival processes where the number of arrival processes scale with SNR, but each of the arrival processes is the same. It remains the same. Okay? So in this case, if you know the literature on queuing literature, you know you can derive large deviations for queues with many flows. Right, so this is the sort of many flow asymptotics that Ganesh and other people have worked out. So in effect, you can actually balance the channel and delay violation probability of errors. And that's the regime I'm interested. I want to generalize and see how much, what conditions, what kind of situations I have scaling of this sort. So roughly, I can say, hand wavy, it is important not only how the mean scales, but also the burstiness, how the burstiness scales. So I'll give you the overview of the result, and then those who are not interested anymore, they can fall asleep and know that they have learned as much as, and then I will be a little bit more technical with the rest of the talk. So we have shown that for arrival processes with light tail, again, it's just a technical term, as opposed to heavy tail, if you know what kind of asymptotics we're interested. So all the processes with light tail, which they have finite means for all moments. Sorry, finite moments for all SNRs. If I look at the probability of violating a particular delay constraint D, the decay rate of this guy depends exactly on how the burstiness of the arrival stream smooths down with SNR. Okay?
Are we looking at the lost model now?
Yes,
Okay.
all of my talk.
So you say, but they're not dependent on SNR, just the sum of, like the number of them is dependent on the SNR.
So the arrival stream is getting bigger and bigger with SNR. The departure gets bigger and bigger with SNR.
The number of processes is getting bigger.
So, I see. For this guy, the number of processes is getting bigger and bigger. Each process is constant. So now I have stochastic processes that interleave very nicely with each other, right? That's sort of the large deviation. So this is going to be one of the examples. But we have shown that you can actually find any arrival process that satisfies slightly less constrained model than this. So this is one example, but you can do it for a larger class of arrival processes. Does that answer? So that sort of made my job easier. So I will look at, in fact, the log moment generating function as a function of SNR, and I look at the scaling of this guy, roughly. That's what matters. So in cases that the delay violation becomes too slow to decay, that will dominate. There's nothing I can do. What I will do is basically the channel errors become irrelevant. I get very close to outage capacity. I go as far as I can from, I'll get myself. Yeah, I go as close to the outage capacity as I can because the error exponent over the channel becomes irrelevant. That's going to be faster no matter what I do. And then I get as many bits as I can through the system. Vice versa, the opposite is true when I get my delay violation to decay much faster than exponential. In that case, I forget about the delay violation. I try to do the best for the channel, which is take the longest the longest number of channel use in every block length, and as far from the outage capacity as I can. In the only interesting case is when we have the burstiness, where burstiness, and my slides are bad, the burstiness, I define it to be the standard deviation divided by the mean. When the burstiness scales down with 1 over square root of log SNR, we have shown that there exists an interesting phenomena where I can actually have two error exponents be available to us. Both of them are exponential decays. I can put them equal to each other and get an optimal choice of R and T. So for this class of arrival processes. So now I have to go and just tweak my model a little bit. So before we would say I have T channel use and I take RT bits out. Now I'm going to take TR log SNR bits out. So now I'm sending proportional to log of SNR, right? So that's my coding scheme. And now all I have to do is to understand the dynamic of this queue, right? And that will be basically, that will give me two exponential bounds that I can balance. Is that clear? So now I'm going to give the math. And I don't expect, a whole lot. I like the intuition, but just in case you're interested about what precisely I'm talking about. So I will look at processes that are all indexed with some index n, which will eventually be log SNR for my problem. And I would say an arrival process is scaling with respect to smoothly scaling with respect to n. If, when I look at its log moment generating function, the limit of that guy behaves very well, and it gives me a meaningful log moment generating function back. Okay? So it's just to say intuitively that as I scale my arrival process, it still depends on log SNR, but if I look at its log moment generating function, it can be decomposed as something that scales linearly with log SNR and another very well-defined log moment generating function. If I can do this, which one class of such arrival processes are the simple summations of exogenous or stochastic processes, then I call these smoothly scaling arrival processes. And now I can use very standard techniques from large deviations of Gartner-Ellis theorem to show that in fact such arrival processes, I can calculate the delay for each bit under such scheme and show that in fact you will achieve a good rate function for your LDP, and I can calculate it. Right? So I have a formula. It's the important thing is to know, and the way that these proofs always work is you have to determine what is the most significant way delay violations will occur, right? So I have to determine what is the most likely rare event that will happen, the dominant rare event. And it turns out in our case, if you think about it, so let's say...
So, excuse me, can I ask a question?
Sure.
In the previous slide, you had this, you're basically formulating the log moment generating function. You have that G event. You are preparing the ground for the functional Legendre transform.
No, actually G event is for, I'll get back to it. It's a simple extension for the case when you cannot balance the two exponents.
So does it have any implications as to what kind of class of processes you are?
Yeah, so basically the simplest is summation of a bunch of stochastic processes, but any stochastic processes that satisfy large deviation principle with log SNR as their index. That's sort of, it's sort of it's a bit of a cheating our way in the sense that we say any process that smooths out as log SNR goes up, I can calculate its exponent and give you the exponent, you can balance them. Any process that doesn't, then we determine which one of the two terms will be dominant, and we throw away the other one and we operate at the best that we could do with the dominant. Right? So that's sort of, so the definition is just to distinguish these cases. Okay, now what happened? Okay, sorry. So what was I saying? Yeah, so what I was saying is in order to calculate this error exponent, again, if you're a queuing person, you would wonder, it's very simple. Let's say the delay budget is a complete multiple of the block length that you're going to design. In that case, the unluckiest bit or the most dominant delay is going to be occurring by the person who just misses the service on the period when you start serving. So you have to show this is a dominant delay violation event, and then you can give the exponent. So as soon as you have the exponent, then you can show that I can calculate the best choice of R and T such that these two exponents are equal, so neither of the two will dominate, right? And I don't care about the formulas. So let's look at an example. I think that will illustrate a lot better the result that we have. Let's say I have what I call a compound Poisson with exponential packet size. So this is a process where I look at any moment of time, a random number of packets arrive, where the random number comes from some Poisson process with rate mu log SNR, right? So it scales with log SNR, while y of t, the packet size itself is exponential. Okay, just the simplest model that you can come up with. So we can see that actually you can easily show, because Poisson is the number, if you increase the number of Poisson random variables and you increase their rate, it's essentially the same thing, that this actually is a smoothly scaling process. So we can show it and find its, basically finds log moment generating function and its conjugate, lambda star. So I can solve the previous problem, find the two exponents, match them, put them equal. All of these large deviation results that we have is across sending the number of flows to infinity. Roughly, you can sort of think about them. So the difference between classical large deviation for large D is that we are dealing with a lot of integer optimization that gives us ugly formulas. So you can relax those integer requirements and get approximations that are very close. And in the paper we compare the result from the two. But roughly you get the results. Now you take this source and concatenate it with a SISO with a fast fading. So now I'm, the longer blocks, I'm collecting more realizations of the channel. As I quoted from Zhang and Shei's result, the probability of error events here are given as SNR to the, minus T1 minus R. So now I go back and put this guy equal to the approximate value, just to get insight to this approximate value, this guy, to get the optimal value of R and T. And I get these two values. Again, I don't think it matters what those are, except for this. So if I look at the optimal coding delay, is a function of mu, which is the mean of 1 over mu is the mean of my packet size. Or in some ways, you can sort of think about it as the burstiness of your source. So T star is a function of your burstiness and your delay requirement. Not surprising. The surprising part is that T star ends up being independent of lambda, which says I don't necessarily care how fast the data comes in, so long as I know what is my delay requirement, as well as how bursty my source is, I can set the block length to be some optimal value.
So is this in some sense a consequence of the higher scenario?
I've been really struggling in the sense that it's not that surprising. If you think about it, if I have a capacity of a channel and I want to optimize my performance, it seems that you can get some amount out of smoothing out the channel by looking at a block size. The arrival rate seems to be it's not that relevant to the information that I need.
No,
the arrival rate will determine what is my coding rate, how fast I get to the capacity.
I was thinking of it maybe wrong. Maybe it's not the way to think about it. I was thinking it seems like sort of the delay is sort of the more, because of the highest SNR regime, are you sort of biasing your results or your design is such that that delay, the delay term becomes sort of more critical?
No, the particular regimes I'm interested, the delay and the channel are roughly of the same order. They're both exponentially decaying in both of those terms. So, with these smoothly scaling processes, we keep them. You're right that if I actually had sent it too fast to too fast, scaled them too smoothly with SNR, I would get the regimes that you're talking about. But yeah.
If you don't scale it, array rate at log of 100%,
if you scale it much faster, you mean, then you will clog up your queue. The delay will go to infinity.
That says it's dependent on lambda. Oh, lambda is independent of.
This is the point. Lambda will determine what is your rate, how effective your coding rate is relative to the outage capacity. So cases you're talking about, R star will go to be exactly equal to the outage capacity. I get and start operating right at outage capacity, right? But T, the block length, becomes irrelevant. Because it doesn't matter how much I smooth it out, I'm operating in a regime that the delay is not, the delay is the bottleneck. I think that's exactly what. Now, sanity check, as you start increasing the burstiness of the source, you sent 1 over mu to infinity, then you will start operating exactly at the maximum multiplexing rate, which is equivalent of saying I'm going to operate at the outage capacity. As I decrease it, on the other hand, when I go to constant bit rate, then my rate will actually get to be as close to lambda as possible. Basically, I have I basically don't have a whole lot of burstiness. I operate at the best coding rate I could be given the chance to operate. So if I draw the optimal negative SNR exponent versus the arrival rate, now I can get a modification of Zhang and Shea's result in the following sense. So this D star now is not the diversity gain of the channel, but the negative SNR exponent of the total probability of error. Says if I have no burstiness or no delay requirement, which is the model that Zhang and Shea study, I get the curve that they give me. But as soon as I increase the burstiness or I make the delay to be tighter and tighter, I actually have to get worse and worse SNR exponents. It's not surprising, right? There is a reliability versus delay trade-off that comes out of such a scheme. Right? Which is somewhat what we were going after getting. So all of these results, none of them are that surprising, but it's a nice way of quantification of results that we were sort of expecting. So how much time do I have?
You can take your time, and people will leave,
They leave. Okay.
Including me. I told you I have to
yeah, no, I thought I was supposed to get right with you.
No,
Depends on, and I don't want to bore the audience.
Suhas will give you a ride if you take longer. Don't worry about it. That's not a constraint.
Okay, so I'll just give another example just to show that the machinery is useful for a whole lot of problems, and we have all these little conference papers that end up being examples in the journal paper. But basically, another really interesting problem that comes out of this is if I have a cooperative network where I have a bunch of relay nodes waiting for helping me to actually transfer my data. Now, I'm going to operate in a complete opposite, so I don't have any time diversity. My time coherence of the channel is much larger than the delay requirements. So I can't really sit on different realization in time. So the trick is, since I don't get enough channel degrees of freedom by looking at time, I actually talk to many of my neighbors. They will all get independent realizations of the channel. So I actually look at the spatial diversity and try to use that for for improving the reliability of the channel. So this is sort of the amplify and forward, the simplest scheme, let's say. Most of the studies in the literature assume that the delay is still large compared to the number of relays you have. Right? So the delay is much larger than the relays, so you actually use all of your relays to help you. The catch is that the coding structures that they propose depends on how many relays you use. If you have 5 nodes, then the codes that you will use are 5 time channel uses, right? So there is the same trade-off exists, which is if I go to a regime where I have now a lot of relays, the question becomes how many of them will I use? Because if I use all of them, all my time will be spent building these huge codes that that govern the collaboration, but which means that my queue becomes very slow and not actually delivered data in a timely fashion.
What is the cooperative scheme?
So the one we looked at amplify and forward, a simple cooperative scheme, because there exists, in the literature, people give the minimum, they call best codes. So these are codes, the number of blocks that they give is minimal for achieving the diversity gain that is proposed. So we looked at these models, and we saw that if you have 2 phases, each with duration of, let's say, I don't even know what new number of collaboration or relays, I would say. So each of my phases consists of these many channel uses for my code. So this is the duration of each phase, and I have 2 of them. And then I get the diversity, which is new 1 minus 2r.
If you have decoded forward, then you can sort of not send the whole code word, you can send just a piece.
Yeah, so I would like to actually, if you're interested, I would like to understand. The problem I have is I would like to use something that gives me, this is how much you need for getting this much diversity. And this was the one thing we could understand. I'm not a physical layer person, so this is the one I could understand. So I'm not claiming this is a good scheme. All I'm saying is you can use the same analysis to ask yourself for this particular scheme, how many relay nodes do I want to use if I have delay sensitive bursty information. Right? So we get curves like this, that if you look at the average packet size versus delay, so this is sort of burstiness versus delay bound. If my delay bound is really lax and my burstiness is really low, I want to use all the nodes that exist in the network. But as I push down the delay requirement, or I make my source more and more bursty, then I have to give up cooperations.
So what is the assumption about all these nodes in terms of their channels?
And this is, I think this is like a slow fading channel.
But they all have IID. So
I think this model, in order to get this diversity, they all have IID channels. Yes. Again, I'm not putting this, relative to the previous slide, has no extra work on our end. It's just saying, if you give me any degrees of freedom that takes some time, I can optimize how much of those degrees of freedom you can use for a particular delay-sensitive information, right? So we did this for spatial diversity with MIMO, and these are just examples of different, But what I really liked about it is that this actually gave us a really nice sort of visual understanding that you don't want to use all of the degrees of freedom if you are really tight on delay budget. So this is a good place to break if anybody wants to sort of run out, and then I will just give a couple extensions. A couple of them are just fun problems that arise when you try to actually do this for something more reasonable. So far I have assumed that there's really one source destination pair of an interest. The reality is in most of network applications, the wireless channel, whether it consists of relay nodes or be it a simple side-step channel, it's going to be used by many users actually sharing that channel. So in this case, the probability of both queuing delay as well as channel errors are now affected by the scheduling that occurs among how the users are actually in a regulated fashion use the channel, right? So for example, for this cooperative scheme, you can ask yourself, if I decide who is the relay and who is the source, I call this the scheduling. The rate of that events occur, the rate of such events also depend on what the scheduling rule is. right? So the objective in this extension that we have just started working on with my student and also Vijay Subramanian is to actually quantify and analyze the impact of various scheduling schemes on the same results that we had before. And then a more ambitious goal is, can we actually optimize and say what is the best scheduling scheme for this particular asymptotic performance that we are interested in. I would, this is just a mark. In all of the scheduling that I talk about, it's just a question of how do I actually get to multiplex the channel. I'm not talking about multi-user diversity where you actually use the diversity to increase throughput. I'm only interested in scheduling from the delay perspective. Okay? And because I don't have channel state information, that's already sort of a moot point. And so we looked at previous Allerton, we looked at a multi-user static scheduling or a round robining and basically apply it to what we had before. So theorems now are only going to be on the queue because the channels, you know, as I showed, is sort of a byproduct of the formulation. We can just plug in any channel and get results. Basically, we could actually generalize what we have to a static schedule. So now the queue will be a batch queuing system with vacations. So what it takes is to actually generalize the large deviation for many flow queue to this particular extension. That seems to be not as that much interest to the queuing theorists, but it's the natural models for communication perspective. We try to do the same thing for longest delay first scheduling, some sort of a dynamic scheduling. And here the situation gets much more difficult because we couldn't exactly, we were still arguing, trying to look at simpler cases. But what happens is I have two sources of bad events. One is I have a whole block, and relative to the end of the block or the beginning of the block, now when I arrive as a bit, I see different delays. Right? That's one difficulty. And the second difficulty is just a large deviation for longest queue first. So combining these two has been a little bit difficult. And all the exponents we have, the upper bound and the lower bound, don't match each other. So, you know, that's if you're interested, let us know. We'd be happy to work with you. And the second piece is all the results I showed were on a simple smoothly scaling. You can generalize it to mathematically more, more general forms where we call it G smoothly scaling, which means you can take care of cases when things are not smoothly scaling. So you get extra conditions on the results, such as these two cases when this function G is either too fast or too slow, where you get the two extreme cases. Either you ignore the channel and try to get the best delay violation probability, or vice versa. I think that should be, yes, that's it. So I managed to